non-Waterloo reminiscing portion of the talk. So thank you all for coming. It's really a pleasure to be hosting Dr. Jesse Hoey here at Microsoft Research Montreal. So Dr. Hoey is, as some of you may know, an associate professor in the David R. Cheriton School of Computer Science at the University of Waterloo, where he leads the Computational Human Intelligence Laboratory. He holds a PhD from the University of British Columbia, has published over 100 peer-reviewed scientific papers, and has received a number of awards, including from Microsoft. You have to talk about that one. The AAAI and the International Association for Patent Recognition, and he's also from the American Sociological Association, and I think he may be one of the only computer scientists that I know of who has 2 articles in the American Sociological Review, which is the best sociological review in the United States, possibly the world. So he's very interdisciplinary. He's an area chair for the International Joint Conference on Artificial Intelligence and was the program chair in the 10th EAI International Conference on Pervasive Computing. And he'll be speaking today on social and emotional artificial intelligence. So please welcome Dr. Hoey.
All right. Thanks, Luke, and thanks for inviting me here and hosting me at this visit. So Montreal is my hometown, so it's always nice to come back here and see how things have changed a little bit. So I'm going to talk to you about artificial intelligence, but my perspective on it might be a little bit different than kind of the mainstream view of AI these days. But I'll start with this slide with some pictures of some of the big achievements in AI. So obviously, artificial intelligence has come a long way from computers that could beat chess grandmasters. This is quite a while ago now to self-driving cars and computers that can play much more challenging games nowadays. But one of the things, if we look at artificial intelligence in group behavior, then the situation looks a little bit different. So this is a picture from the 2017 RoboCup, which is probably the quintessential sort of multi-agent problem. And these robots are playing on a team, and so it is sort of funny because they're robots and they're a little bit difficult to maintain standing and things like that. But they do know that they're playing on a team, and they probably have some kind of centralized controller, but they really have no notion of what being a team member means, right? And what they essentially lack is any kind of idea of empathy or culture, emotion, or altruism. So they don't have a way of kind of interpreting what other agents are, how other agents are handling the situation as team members, as a social group. And there has been some efforts to make this happen. So let's try to put some emotional behaviors into our robots. So here's this guy he's happy, and now he's not so happy. Maybe he let in a goal or something like that. But of course, these are just purely scripted behaviors, right? This robot has no idea what this means to any other robot. And in fact, no other robot has any other way of interpreting these signals, okay? And if you look at humans when they play games together, you see this vast array of emotions going on. So this is a short clip from the Barca junior team that just beat this Korean team. And you can see this incredible array of emotions going on and different cultural signals that they're sending to each other. Like this guy is using the face slap, which must be some kind of Spanish, expression of empathy. I'm not sure it works so well with these Korean guys. There he's trying to. So, anyways, so the bottom line is that artificial intelligence has come a long way, and we can do some remarkable things with it. But when we get to the point where AI or robots or artificial intelligence systems are trying to interact with humans or with groups of humans, the situation looks quite different. And so this is sort of a well-known problem. If you look at self-driving cars, for example, self-driving cars have some difficulty when they get to busy intersections, for example. And one of the reasons that they have difficulty is that they can't display enough aggression to get through the intersection, right? So this cartoon by the Oatmeal is meant to sort of lampoon that a little bit. And this is a situation where this Google car is trying to negotiate passage with this human through an intersection. And you've probably all been in this situation where you don't know who's going to go next, and somebody's got to kind of take the bull by the horns and kind of drive forward. And that aggression level is a culturally determined thing. So if you go to different cultures, people have different ways of doing it, right? And so in this situation, the human's like making this way too complicated, and the robot has no idea of what's going on. The bottom line is that these robots, these self-driving cars, have no model of how a human works. Okay, so they have no human model in them. They have models of how things move in the world, but they don't have a model of something like the level of aggression that's needed to get through an intersection. So artificial intelligence has taken a stab at putting emotions into artificially intelligent systems. And this is sort of coined, this a term that's used to describe this as affective computing. So here I have a picture of, I don't know why I put von Neumann there, but anyways, there he is. And he didn't work on emotions so much, but Herb Simon was probably the first person to think seriously about how could you put emotions into a machine, and what would that mean? And he basically described emotions as being something that disrupts cognition. Right? So we're thinking all these high-level thoughts and we're reasoning about what to do next, and then emotions come in and sort of kind of disrupt everything. But the disruption is there for a reason, right? It enables us to better coordinate with other human beings, for example. And then Roz Picard wrote the book on affective computing in 1997, and the book starts with this quote. This book proposes that we give computers the ability to recognize, express, and in some cases have emotions. Is this not absurd? Right? So in 1997, this was, nobody had really thought this before or written it down, and it did seem very absurd, but she was a professor at MIT, so she could get away with saying absurd things, I guess. And since then, the field has grown, and there's now an IEEE transactions on affective computing, and there's a couple of major conferences. So there is a fair bit of work in the area. And Roz Picard gave a talk at AAAI in 2017, describing some of her amazing work on using wearables to detect emotions for healthcare applications. And they've really done some amazing things in doing that. But if you look at artificial intelligence, so for example, in the 2017 AAAI, I looked through all of the titles when she was giving this talk and found the word emotion appeared 3 times, right? That's 3 times in about 1,000 papers. And the same thing in 2018. And so I sort of feel like this study of emotions has sort of been pushed a little bit to the side by a lot of the recent developments in AI. But it'll make a comeback. Okay, so I think that the view that Herb Simon proposed, which has sort of been largely what a lot of affective computing has worked from, that emotions are sort of disruptors of cognition, I think that this may actually be fundamentally backwards. And I'll try to explain why, and then I'm going to give in this talk a model that I think puts the horse before the cart instead of the cart before the horse. So I'll try to motivate it with some evidence that we have from neurophysiology. So this is a very, very highly stylized picture of what's going on in the human brain, and from this paper by Zhu and Thagard. And what they do is they describe 2 different systems that happen in human cognition. And they call it a low road and a high road. And the low road is something that these are both cognitive processes. So these are not instinctive things. These are actually things that humans reason about. But the low road is something that avoids the large parts of the sensory cortex and is something that happens very, very quickly and is able to give human beings a rough idea of what to do next. Okay? Then the high road is a pathway through the brain that takes longer, but then it goes through these cortical reasoning aspects, and that's where you do your actual sort of cognitions and thinking about how the world works and so on and so forth. The interplay between these 2 systems is really quite an interesting part of how humans make decisions and act in the world, with, again, this low road sort of providing this very fast, sort of quick and dirty solutions to things, and this high road coming in later, if necessary, and kind of trying to fix things up, right? You see the same idea of two systems coming out from psychology and behavioral economics. So perhaps the most famous example of this is this book by Daniel Kahneman, Thinking Fast and Slow, where he describes these two systems again, the fast system 1, which operates automatically and quickly, and then the slow system 2, which is effortful mental activity and complex calculations. And the way that they work together in Kahneman's work, or how he describes it, is that this system 1 is the thing that is always in operation that humans are using to get by, and then when that runs into trouble, people call this system 2 into play in order to help them figure out what to do, right? But people do not want to go and use this system 2 because it takes more energy. Okay? If you can avoid using it, might as well. You get by with much less if you can go with this. And you see the same idea throughout a vast array of different disciplines, people running into the same concept of these two systems in the brain. All right, so this is the sort of what I see as the traditional view of emotion in artificial intelligence, which essentially is what Herb Simon was talking about. So you have some of the environment, you perceive what's going on, then you have your cognitive systems that are reasoning about the environment, what's happening. So you're playing chess and you're figuring out where all the chess pieces are and how you're going to move them and so on. And then that drives you to take some action. And then your emotions are things that are happening kind of on the side after the fact. So after you've sorted out everything that's going on in the world, then you figure out what emotion you should be feeling, and then you sort of have that emotion, and that can modify how you're thinking about the task that you're doing. So really a cognitive machine disrupted by emotion. And again, these disruptions that the emotion causes may be useful, right? They may be actually pointing you in a direction that may be useful to go, but really they are take second place to this sort of higher level cognitive reasoning engine. The theory that I'm going to describe today really reverses these two systems, and I think puts the affective processing system as the thing that has the first kick at the can, so to speak, right? So these perceptions come in, they go straight into our affective reasoning engine. This generates an immediate action. This is what I should do next, okay? And the key behind this affective reasoning engine is that it provides an action, a course of action to take, which is the one that is most socially reasonable in the situation. After that, if this breaks down, then people can call in these higher level cognitive processes in order to figure out how to fix this, right? So, okay. So that's the sort of very high level view. This is an emotional machine which is disrupted by cognition. Yeah.
I'm trying to tease apart what is affective here and what is just sort of a quick like muscle memory. Like I've gone through this computation already before.
Right.
We're separating those two things.
Yes, we're separating those two. So so I guess there's actually a third system here which I'm not putting in, which kind of bypasses all of this, right? So you could draw another arrow that is just immediate. So that's when if I jump at you and you jump back, that's your sort of instinctive muscle memory to avoid things coming at you, for example. That's not what this is talking about here. This is still a cognitive process. And the theory that I'll describe to you is this cognitive process relies heavily on language, so on how we interpret the world in terms of symbols, essentially, right? Or, linguistic concepts. So, okay. Any other thoughts or questions? Okay, so I'm going to now describe to you this theory, and then I'll give you a few examples of how I've gotten it working in a couple of different contexts. So how we're going to do this is I'm going to look back at this work by Osgood in the 50s. So Charles Osgood was a psychologist who did these amazing experiments, and he went around the world and asked people to rate concepts, so basically words in the language, but he did this in many different cultures, so different languages. And he got people to rate them on what are called semantic differential scales. And semantic differential scales are just a scale with two opposing words at each end, right? So angular to rounded, or weak to strong, or rough to smooth, right? And he asked people, he'd give them a word, like in this case the word polite, and say, put a check mark on each of these scales where you think politeness sits, okay? And what's amazing is that there's this incredible degree of consistency amongst humans that share the same language, that are in the same cultural group, as to where these words should go. So this picture shows one of the diagrams from his study in 1952 showing two groups of 20 people. This is the mean of two groups of 20 people. And you can see this amazing degree of consistency. Everybody agrees, right? So what's amazing about that is that if you look at the word polite and you look at some of these scales, so you might wonder, well, what does politeness have to do with being rough or being smooth, right? Like, it seems to be unrelated in some way, at least on a sort of semantic level, but everybody agrees, yeah, politeness is more sort of smooth than rough, right? So there's something really interesting going on here, that everybody has this implicit, that we all share these ratings of things on these different scales. So what he did was, he did these studies, and he actually used many more dimensions than this. So there's, I think, on the order of like 150 dimensions that he used, so 150 of these scales. And then he went back and did a dimensionality reduction and found that he could account for over 80% of the variance in all this data with just 3 dimensions, okay? And the 3 dimensions are 1 dimension of evaluation, good to bad, 1 dimension of power, so strong to weak, and 1 dimension of activity, so sort of hyper to asleep. And I'm going to put this one coming out of the board. So bigger things are more hyper. And so when you get people to rate words, they all agree on where they should go in this 3-dimensional space. So for example, being polite is good and kind of powerful, and being abusive is sort of weak and bad and really active, right? So this is a bigger word. And being serene is good and kind of weak and really inactive. And you can do the same thing with identities. So students and professors, for example, this is a good example. So students are, everybody kind of agrees that students and professors are about the same goodness, right? But maybe professors are a little bit more powerful than students, and students are maybe a bit more active than professors, right? And this is culturally dependent, right? So if you go to Japan, for instance, then professors are typically seen as significantly more powerful than students, right? So, but if you come to North America, then this has sort of become normalized. Students and professors are seen as much more equal on this power dimension. And behaviors as well, so apologizing to somebody and fighting with somebody, and so on. So this is actually real data taken from a study done in 2003 in the United States. So these are the means of, I've put the words at the means of where people would rate these concepts. Again, I'll just reiterate that the important thing to remember here is that everybody in the cultural group agrees on where these words should go in this 3-dimensional space. Okay, so how we're going to take this idea and leverage it and turn it into a control principle that we can use to drive an artificial agent. And we're going to do that using this affect control theory. And what affect control theory says is that people carry around these fundamental sentiments. Okay, the fundamental sentiments are these things here. This is everybody's agreement on where things should go in this very simple, just 3-dimensional space. When a social action occurs, so something happens in the world, so for example, maybe in this case here we have a nurse, and here's a nurse sort of dumping some water on this guy's head, and here's a nurse helping this lady, for example. These social actions create what are called transient impressions. So the transient impressions are also culturally shared things They are how you feel about the situation, so how you feel about these things in context. All right? And the transient impressions may be different from these fundamental sentiments, and the difference is called the deflection in this theory. And the affect control principle says that people try to experience events that confirm fundamental sentiments. So essentially, they try to reduce this deflection. So affect control theory is a consistency theory. It says that people will basically do the thing that sort of leads them to situations where things are emotionally consistent, and the consistency is defined by a culturally shared construct, which I'll show you in a second. So I'm going to go through a couple of levels of sort of increasing detail of this theory, and this is sort of at the highest possible level. But interrupt me anytime if you have questions as we go. But I'll show you a bit more detail of this as we go along. It's all described in this really nice book by David Heise, who's the guy who's done many, many years of work on this theory, starting from the work of Osgood and many others as well, and described in this really nice little book called Expressive Order. One of the interesting things about this book is that it sort of has two parts. The first part is all the social psychological part, and it's just, it's text, and it describes his work in looking at a variety of different cultural groups and how they follow these kinds of dynamics. And then the second part is a mathematical model, okay? And what's sort of interesting is when you talk to most sociologists, they've sort of all read the first part of the book, but kind of ignored the second part. So they don't tend to be they don't tend to have that sort of math background. And when I read the first part of the book, and I was like completely lost. I had no idea what was going on. But then I read the second part. I was like, oh, this makes total sense, right? So this is why it's good to have a multidisciplinary group working together. All right, so here's a little bit more detail. Affect control theory uses a very simple grammar of an actor behaving on an object. The object is often another person, right? People have these fundamental sentiments about each of these three things, right? So this is a 9-dimensional vector, and it's, according to the theory, these vectors lie in the range minus 4.3 to plus 4.3. And I've asked every sociologist I've met who works in this theory of why it's 4.3, and nobody seems to know. I think it's lost in the sands of time, but it does have something to do with Osgood's original experiments. It's actually not important, and the versions that I work with is not restricted to be in this range, and you could rescale it to be anything you wanted. Okay, when you see an actor behaving on an object, it creates a transient impression for each of them as well, and this is again gives you a 9-dimensional vector in the same space. The predictions of the transients from the fundamentals are given by this nonlinear operator, which I'll show you in a second, and this is something that is also culturally shared. Everybody agrees on how these impressions are created. The deflection is then just the Euclidean distance between fundamentals and transients, and the affect control principle says that actors work to reduce this deflection. All right, so you can use this as a control principle because you can say part of this, these sentiments is a behavior. So you can say, what is the best behavior to take in order to make this actor and this object agree sort of emotionally to be doing something emotionally that's consistent. Okay, so you can use this deflection measure as an optimization surface that you can walk down to find the optimal behavior to take. Affect control theory also has a very precise definition of emotion, which is remarkable. This is, I think, the only theory I've ever seen that has such a precise definition. The emotions are described as being proportional to the vector difference between fundamentals and transients. And people use emotions as a communicative signal to tell the person that they're interacting with where that person is getting it wrong, right? So if I'm interacting with you and you're not treating me how I think I should be treated in this situation, I'll send you an emotional signal in order to help you correct for that and so that we can come to an agreement on how we're supposed to be behaving. Yeah.
I guess a vector?
It's a vector in the same three-dimensional space, yeah.
And so, yeah, I guess different emotions like happiness, sadness.
Yeah.
I think are these points in space or
That's
dimensions? Okay.
Yeah, there would be a point in the space, yeah. And if you look back at here, that's why these emotion words are in the same space, right? So the nice thing about this three-dimensional space is that you can compare all these different entities in the same space. So behaviors, identities, emotions, they're all comparable directly, right, with a simple three-dimensional vector. Okay. All right, so here's the little bit more detail. So we have a social interaction happening here. Here's our nurse and our patient. We've already done a population survey, so we've asked people, well, what do you feel about a nurse? Okay, and we've gathered a rating for nurses, which is this one here. So nurses are seen as 2.9, 1.5, 0.2, for example. And then we've asked them about patients, and patients are a little bit less good, much less powerful, and much less active. And how about comforting, the behavior of comforting? Well, that's positive and powerful and not very active, right? Given these fundamental sentiments, we compute a transient impression for each of the three, and the transient impression is given by a series of equations with polynomial features in them. So the polynomials are basically, these polynomial features are combinations of these different elements in the fundamental sentiment. Okay, so this one here is the evaluation of the behavior multiplied by the evaluation of the object, and then it has a positive coefficient, and that's the effect on the evaluation of the actor, right? So what this term says is that if the actor does something good to a good person, then they will seem more good, right? These coefficients are things that are also culturally shared and measurable. So we can ask people, how do you feel about a nurse? How do you feel about a patient? How do you feel about the act of comforting? How do you feel about a nurse when you see a nurse comforting a patient? Okay? And that measures this transient impression, and then they can do a regression and find these coefficients and find that they are, again, shared culturally. All right, so the difference between these two things is the deflection. And like I said before, I can use that to predict the next behavior, so I can optimize over this deflection measure in order to compute the best behavior to take. I can also compute a re-identification of the nurse and the patient. So I can say, if I see somebody comforting a patient, who might that be? Well, that's probably a nurse, right? So I can do that as well. Okay, before we go to an example, which might help clarify some of this, any questions? All right, so let's walk through an example. We'll use this nurse-patient example. Here's our nurse and our patient. Again, here's their 3D evaluation, potency, and activity fundamental sentiments. And remember, these are culturally shared. I'll just keep reiterating that so we're sure we remember it. The nurse is up here, and the patient is here. The important thing is that the nurse knows that she is here and knows that the patient is here, and the patient knows that she's here and knows that the nurse is here. Okay? They both agree on that. So I can compute, well, let's see what happens if the nurse comforts the patient, right? So I compute the transient impressions, which are in light blue, and you can see they're quite close to the fundamental sentiments. And then I can compute what emotions would be felt and communicated. The nurse who comforts the patient would feel compassionate, and the patient would feel serene. Okay? And the deflection is low, it's a 1.3, so that's a low deflection. But let's say we make the nurse ignore the patient, right? So here's a nurse who's ignoring a patient. Ignoring is quite negative and not very powerful. Now the nurse seems much more bad than a normal nurse would seem, right? We'd say, well, who's this? This is not a very nice nurse. She's ignoring this poor patient, right? But the patient also seems more bad because, well, maybe this patient's been a really nasty patient, right? And that's why the nurse is ignoring her. So we construct all of these things, but we do so just by computing these transient impressions. It's a very simple calculation. The emotions that would be created are agitation for the nurse and indignant. The patient feels indignant. How dare you ignore me? I'm the patient, right? These are the signals that each would send to the other in order to correct for this. So the patient would send this vector to the nurse and say to the nurse, essentially, by sending that emotional signal, which humans can do very, very quickly, hey, listen, I'm supposed to be up here, and you're treating me like I'm down here. So, and I'm telling you exactly how you're treating me by sending you this vector. And the nurse can take that and say, oh, right, I got it wrong. I thought you were a horrible patient, but really you're not, right? So I'll correct for that and do something to make it better. Deflection's high.
Deflection mean on the behavior? Like you have ignore, remove, ignore. So if you were like ignore again.
Yeah. So what it means on the behavior is that you may reinterpret the behavior, right? So if you're seeing this happening, then you're like, well, maybe I'm sure that's a nurse and I'm sure that's a patient. Maybe she's not ignoring the patient, right? You seek an interpretation of the situation that makes it emotionally consistent, right? So the transient impression would be one way of getting that from the behavior, right? So for example, this has gone, what you can see here is this has gone up in evaluation, right? And it's gone up in power. So one possible, so that's saying, well, maybe this is not, I don't know what word would be close to this transient impression, but it's probably something less like ignoring, something more positive, right? Well, maybe she's busy and just we'll come back to this patient later or something like that. Does that make sense? All right. Here's another example. This is a student and an automated tutor. So this is one of the early examples that we built with this theory. And the student and the tutor this is kind of like student and professor, right? They're kind of in the same spot, but maybe the tutor has a bit of power over the student. So we can compute, well, what would a student do to a professor? Well, the student would do something like this EP and A rating. And I can look up in my dictionary of sentiments that I've had rated by people and find this behavior. Well, the student might ask something to the tutor. And then the deflection is low, the transients are close to the fundamentals, and everything's good. What if the tutor yells at the student? Okay? This creates transient impressions that are very far from these fundamentals. So maybe this student is really, a lot more, this is a bad student, or maybe this is a horrible tutor, right? And then the obvious, what emotion would be felt? Well, maybe this tutor is angry, and this student would be exasperated or remorseful. Then we can compute, well, what would the student do in order to try to correct for this situation? Well, they would maybe listen to the tutor and feel self-conscious, and this act by the student would help it to restore his transient impressions back towards his fundamental sentiments, but not so much for the tutor because the jury's still out. The student doesn't know maybe this tutor is really a nasty tutor after all. But if the tutor then does something, so this is the computation, the optimization for the deflection, so it's minimizing this deflection. Well, what would the tutor do? Something like apologize to the student, and now they've sort of managed to get back to somewhere where the deflection is fairly low. Okay, so what I did here in this example was I forced the tutor to yell at the student. That's not an action that affect control theory would compute because it creates so much deflection, right? So I create that artificial action and then compute what's the optimal thing for the student to do to try to fix things, and then what's the optimal thing for the tutor to do to try to fix things even more. Yeah, there could be circumstances where it's appropriate, yeah, and people could yell at each other for a variety of different reasons. One of them is maybe not yelling at, maybe that's a little bit too strong. Yeah. One of the things that happens when deflection goes up is that this system 2 thinking kicks in, right? So when there is a inconsistency on the emotional, so the basic idea is that if I'm operating, this is sort of like an equilibrium theory, right? So if we're on the same page and we're operating according to this emotional model, as long as everything stays at that equilibrium point, then we'll just keep doing that, right? It's really easy. You don't have to think. You just have to operate in this simple three-dimensional space. As soon as things go off the rails, though, then you kick in this higher level cognitive reasoning, right? And one of the things that that might help with is that it might force the student to actually think about what they're learning, for example, right? And then they'd actually consider it and take the information in instead of sort of just ignoring it and pretending like everything's fine. So that could be one reason, yeah.
So just I guess maybe to continue along the line of what you just said, does that sort of, is there an implication maybe that, you know, in some scenarios there's utility in having high deflection because it forces you to engage that higher level system and start thinking more deeply about something?
Yes. No, there could be, for sure, yeah. And I'll talk about that a bit more in a second, but affect control theory doesn't have a utility function, right? The version that I've developed, which I'll show you next, does, but affect control theory is only describing what's happening at that equilibrium point, right? So let's talk about utility again after I show you BayesACT.
Yeah, I was thinking whenever a student is staring at you.
Right.
So the teacher needs to
Right.
have something with reflection to get the student back.
Yeah, that's. But a student staring at the window is not being a very good student, right? So they're already off the that equilibrium point, right?
I'm just trying to think of it. Is there a circumstance where an action is negative in one context but positive in another?
Yes, I mean I'll try to think of a good example there, but.
Brings you to equilibrium is appropriate in any action.
Yeah.
Brings you not. So like, we're just looking at yells at, brings you like lower left quadrant. So if the student was in like the upper right,
Yeah.
it would seem like they yelled at would bring them to equilibrium.
Getting a transient that is here from here is only based on this point. So if the student was actually up here, then yelling at wouldn't necessarily bring them in the same spot, right? Okay. But you're right. It could be something along those lines, right? And maybe a better example is the work that's done in cognitive therapies for depression. So a depressed person is someone who has a very negative sense of who they are, right? So they feel kind of negatively about themselves. And for many years, people thought that the way to handle this was to blast the person with positive thoughts, right? And that doesn't work very well. And the reason it doesn't work very well is because you're not treating the depressed person like a depressed person. That's how they think they are, right? And so you have to. So the self-verification theory came along and said that, well, what you need to do is agree with the person that the world is terrible and that everything sucks, and then you say, yes, this is the way you are. I am verifying your sense of who you are as a depressed person, right? So I'm performing negative actions, but I'm doing it in a way in order to get us basically at that point of emotional alignment. And then from there, I'm going to slowly try to work you in a direction where you hopefully become less depressed, for example. That make sense? Okay. All right. So my work in this has been to develop a version that adds a couple of new pieces to this. One is a utility function, and the other one is modeling identities and behaviors as probability distributions, right? So of course, it's not the case that everybody does agree exactly on where these concepts sit in this three-dimensional space. So when you make these measurements, you actually get a fairly big variance around the mean. So everybody does agree on the mean, but there's a lot of disagreement on where they would go, okay? And this variance turns out to be very, very important. So it's something that people, I believe, use in order to handle operating in groups, right? So the problem with group behavior is that everybody's different. There's this diversity, right? We aren't, even if you're in a single cultural group, so we as academics are often in groups that involve many different cultures, But even if we're in a very uniform cultural group, there's all sorts of differences because people are interacting with each other in many different circles and in a sort of maybe in a small world type social network. Because of that, there's lots of uncertainty that comes into play, and we need to be able to model that uncertainty in order to use this kind of idea, this emotional consistency to cooperate with other people. Okay, so those are the two pieces, and I'll walk you through how this works as well. I have quite a number of papers on it, but two of the journal papers, one in artificial intelligence, and the other one, as Luke pointed out, in the American Sociological Review. And this paper won 2 awards at the ASA meetings in 2016. All right, so the model is based on a partially observable Markov decision process. So I'll give you what this is all about, and then we'll see how we can fit this affect control theory piece onto a generic model of how an agent interacting with the world. So a POMDP, or partially observable Markov decision process, consists of a set of states X and a set of observations that we can make about those states. So these are unobservable or latent states. A set of observations. We have an observation function, which is a probability distribution relating these two things. There is a set of actions that an agent can take that change the world according to some transition function, which is another probability distribution. And then we have some reward or utility function that describes the agent's preferences over these states, right, using a numeric scale. Okay, so that's the generic model. And you can use this to do a number of different things. And maybe the simplest way of visualizing how you can use a POMDP to generate a plan is to just do a very, very simple forward search. Right? In general, this doesn't work, but this is a way of describing what you actually are trying to do. So here we are in our current state. And remember, this state, since this X, our sort of interpretation of the world, is latent, we can't observe it directly, then the state that we're in is actually a belief state. So this is a probability distribution over all possible states. From this state, my agent has a number of different actions that it can take, which lead it to another belief state after taking the action. And then the other person that the agent's interacting with has a bunch of things that it can do, and that leads to another state, and so on and so forth. And down somewhere in this tree is some rewards, let's say, and then I can draw this whole tree out, find these rewards, and then propagate them back up through the tree, weighting them by the probability of these things happening, and then I can use that to rank the actions that my agent has and pick the one that optimizes over the utility function. Okay? So that's just basic Bayesian decision theory. All right, so what's the problem with doing this, of course, is this tree, you can't write it out. It's way too big. And these branching factors are colossal, right? And so if you tried to do this, you'd rapidly run into major problems. And a lot of the work in reinforcement learning and decision theory is how do you expand this tree in a smart way so that you don't wind up having to draw the whole thing out. So for example, you can do things like say, well, as far as what the other person's going to do, I'm just going to ignore all the things that are really unlikely. Okay, that could reduce the branching factor here by doing that. But this branching factor is much harder to handle because I can't ignore any action that I have available to me. And the reason is if I ignore one action, it could be that that is the action that leads to an infinitely higher reward than anything I've seen before. Right? And so that's the reinforcement learning problem. I've got to try them all. If I don't, I might miss the one that is going to be, utopia for me. All right, so now we're going to put in this social and emotional reasoning engine and see how we can use that to help us guide that action selection. Right? Remember back to the start of the talk, we talked about this emotional reasoning engine is going to sort of tell us roughly what to do in order to get by. Right? And then we're going to do a bunch of maybe cognitive calculations after that to help us out. So I'm going to take my basic POMDP and I'm going to just make a slight modification in order to make the presentation a little bit easier. I'm going to add a random variable that describes my own action. Right? And I'll call this B prime. And it's just deterministically set by A. Okay? So this is no change at all in the model. I'm just adding this one random variable. And then I'm going to layer in a set of random variables, one for fundamentals and one for transients. And I'm going to connect them through time. Okay, so the transients are going to evolve through time according to this impression formation equation. So I say, well, what do I expect the transient impressions to be after I see an event taking place? The fundamental sentiments will evolve through time as well. I will admit the fact that these fundamentals may be changing slightly. So if I, for example, go and start living in a different culture, then I need to sort of shift my fundamental sentiments a little bit. So I'll admit that may be happening. Then I have this red link between the two, which is my affect control principle. It says that I believe that fundamentals and transients will be close together. And then I have these green links, which are my shared cultural sentiments about things. So essentially saying that things in the world have fundamental sentiments. Okay? And that's another probability distribution, and that can take into account the variance in these fundamental sentiments. So given all that, I can combine them together and compute a probability distribution over fundamentals, given all of these things, and then I can integrate out the identities and create a distribution just over the behaviors in this three-dimensional space. Okay? This probability distribution I've actually labeled as pi because it's a policy in a way. It tells me what to do next. This is a probability distribution in EP and A space, but it's telling me this is the emotional signature of the thing to do next in this situation, right? As a probability distribution. So then I can draw a sample from this, and that's the thing I should do next, right? Or I can seek the maximum or something like that, right? That makes sense? Okay. All right, so how does this help us? Well, essentially, from a belief state, it tells us this function here says, well, you know what? You don't have to actually consider every possible action. You should consider actions only that have this emotional signature, right? Because those are the ones that make sense to the people that you're interacting with. They're the socially acceptable behaviors that you should be taking. So the way I imagine this is that, imagine this huge tree is in the dark, which it is, right? Because we can't draw the whole thing out. And this affective reasoning engine is like shining a beam of light down through this tree. Okay, so it's saying, these are the things you should consider next. Don't even think about these things over here, right? So it's an attentional mechanism. It's not a way of ranking all of the actions. It's a way of saying, if I draw a sample from this distribution, I'm going to get something that's in this flashlight beam. And the things in this flashlight beam are the things that are going to work at this emotional consistency level. Okay? So essentially, this is a way of solving this problem by having this shared cultural information on the side that we're using in order to guide attention. Okay. This same idea actually comes, you see it in another branch of sociology called practice theory, which is sort of fairly far removed, it seems, from affect control theory, or at least the practitioners of these theories would say so. But what's remarkable is that Bourdieu, who's maybe one of the big sort of originators or thinkers in practice theory, described something called the habitus, which is very, very similar to what this is doing. So I'll just read you this quote. Responses of the habitus may be accompanied by a strategic calculation, but these calculations are first defined without any calculation in relation to objective potentialities immediately ascribed in the present, things to do or not to do, things to say or not to say. Okay? So those immediate, those objective potentialities are, we can describe them mathematically using this affect control theory. Okay? And what he's describing this strategic calculation is that this flashlight beam is not just illuminating a single action, it may be illuminating just a couple of actions, right? And within the flashlight beam, I can then use my cognitive reasoning processes in order to try to find what is the best actual action to take in order to optimize over this utility function, right? So this, we get back to the utility function that you were asking about earlier. I'm still going to try and optimize this, right? But I'm only going to do so within this subset of these branches of the tree. All right? So the idea is that the humans will only do this if they have time. Right? Time is an important thing. If time runs out, I've got to act, then I'll just do the thing that's most emotionally consistent. If I have time to sort of think about it a little bit, then I'll wind up maybe finding something that benefits me a little bit more. Right? People that do too much of this tend to sort of throw things into disarray in social situations. But it goes very much in line with what Bourdieu was talking about, I believe. Okay, so that's all the sort of the model presentation that I'll give, and I'll walk through a couple of examples. Actually, I'm already almost out of time, so I might just go through the first one and then briefly the second. But any questions about the model? Yeah.
Just going back to these original sort of three-dimensional embeddings, let's say, of words that come from BayesACT, how much coverage of like the lexicon do you have there? Like how many words have one of these associated three-dimensional embeddings?
So there's a number of different. It basically depends on how much money you want to spend on your study, right? But the sociologists have gathered large dictionaries. So the most recent one that was gathered has, I think, 800 or somewhere around 800 identity words and 800 behavior words, and they're rated by on the order of 50 individuals each one. So you have a pretty good sample of how people feel about it. Yeah. So those dictionaries exist. There's also bigger emotional dictionaries that are on the order of maybe 10,000 words or something like that, but not gathered by these same affect control theorists. So.
Yeah, I'm just thinking about like, could you tack on these sort of ACT embeddings to what we use more regularly with word embeddings and think about emotional language modeling and these sorts of things?
Yeah. Yeah, so I've had a few students work on that problem, and I know a few people who are working on it. So exactly that idea is that take a word embeddings model and somehow also integrate this. It may be the case that if I construct let's say a 300-dimensional word embedding, that these 3 dimensions of EP&A are in there somewhere, right? And so it's not altogether clear that is happening though, because you wind up with like the movie. Word embeddings trained on movie ratings, for instance, you get the word good and bad are really close together, right? Because they are used in very similar contexts. Yeah, that's right. Yeah. So I'm not clear on that yet, but yeah.
So actually on a similar topic, these relationships are highly contextual, right? So for example, the tutor compared to the student might be much more powerful, but compared to the tutor's boss, that person is suddenly just some high school kid.
Right. Yeah.
If I understand correctly,
I'm already blanking on the terminology you're using. The initial emotional affects embedded in this two-dimensional space are not dependent on these relationships, right? There's just a word for tutor.
That's right.
So have you thought about how to do this or think about this in the context of those changing relationships?
Yeah, so I mean, the theory says that it is a linguistic theory, really, at its core. So the sociologists describe this as called symbolic interactionism. So it is based on symbols. So if the concept is that let's say I walk into a hospital and I see a guy, a person in a white lab coat, right? I will sort of, my cognitive process will say, oh, doctor, right? This is a doctor. And then I'll associate an emotional fundamental sentiment with doctors, right? This is how I believe doctors are. And then using that, I'll compute what I think this doctor will probably do to me, right? But that concept, that fundamental sentiment, is going to be the same in any context, right? So if I see a doctor when I'm taking the subway, then it'll still be doctor, but then it'll be doctor on the subway, right? And so that additional context I can put in as well, and that context would change things further. So let me reiterate that. When I described ACT, remember we just had this three-dimensional grammar of actors behaving on objects. So I can augment that, and then this has been done with a fourth thing, which is the setting or the context, right? So I can say actor behaving on object in some setting, right? So student joking with professor in the classroom is different than student joking with professor in the bar, right?
And that context might include other actors or objects. But wouldn't it be more natural to include it in the state information in the MVP? I mean,
Because it's changing over time. I mean, just listing a single. I mean, you can embed the entire state within this context, but that seems much more difficult to do than to just have the relationship, the emotional content be able to change over time.
Yeah, so the tricky thing is that the state of the MDP, right, this underlying denotative state, this X, can be very high dimensional, right? This element here can get really complicated, okay? But the key thing is that these pieces here always stay the same. They're always in this three-dimensional space, and they're comparable within that three-dimensional space, right? So I don't have to model all of this context if I can just get this emotional meaning of things. So I can compute a whole bunch of things just with the emotional meaning without having to figure out how the world works, right?
Offline.
Okay. So I think I'm out of time. So I think I gave this much more slowly than I usually do, but that's. What do you want me to do? Should I?
maybe a brief example and then
Okay.
questions.
Okay. I'll skip this prisoner's dilemma stuff, but this is sort of a canonical, the sort of minimal working example of using this theory in practice, and I can actually show you a demo of this game play if you'd like after the fact, and I'll describe the other piece that I wanted to mention was the Themis.cog project. This is a project that's in collaboration with my colleague Tobias Schroeder, who was the guy who introduced me to affect control theory, and he's in Germany at the Potsdam University of Applied Sciences. Kim Rogers, who's a sociology at Dartmouth College, and May Nagapan, who's a software engineer at Waterloo with me. So this is funded by the Transatlantic Platform Digging Into Data Challenge. And what we look at here is we're looking at interactions of people on online collaborative networks like GitHub, for example. So that's our primary sort of target. So we look at people interacting over pieces of code on GitHub, and then we're really interested to find out how do these social and emotional factors come into play when people are trying to actually do something together in a social network. So I won't give too many details about that, so maybe I'll just skip these last bits. This is the affect control theory version of the group simulator. So I can create instead of just doing an interaction between two agents, I can do an interaction between a whole group of agents. And then the blue agent is the sort of everybody's concept of the group as a whole. And I can use affect control theory to compute not only what people will do to one another, but who they will do it to. Right? And the basic idea is that people will try to interact with other people that are going to help them sort of confirm their sense of self the most. So we can do some pretty interesting group simulations with this. Then we've gathered some data sets as well. So a few data sets we have a new data set of these ratings of actually GitHub concepts. So we're interested in trying to find out how do developers on GitHub rate concepts on GitHub. So for instance, the word commit means something different to a developer than it does to someone agreeing to be married, let's say. And these were rated by 50 GitHub developers. And then we've done some work on trying to do some sentiment analysis. So based on pull request comments on GitHub, can we extract these three-dimensional vectors from that? And then we have a few other data sets as well that I've been working with. So the basic idea here of this project is we're going to have all this data coming in. We're going to use some NLP to try to uncover what's going on, but we're going to guide that using this affect control theory and hope that the two things meet in the middle. And then that will allow us to analyze these different biases that are present in these social networks, and possibly also allow us to design interventions and then artificial agents that act in the networks in order to help the groups become more effective or have fewer biases, for example. Okay, so just to sum up, a lot of artificial intelligence is sort of, I believe, sort of equating intelligence with decision theoretic rationality. But we really know that emotions are necessary for intelligence, and this low road gives a heuristic social intelligence, and that social intelligence allows us to solve social dilemmas, like the tragedy of the commons, for example. AI may be sort of pure, traditional AI. People might say, well, you know, this is just, the reason that we have these emotions as humans is just because we're so dumb, right? If we just need to have bigger brains, and then we could do everything decision theoretically, and we'd be all set. So I think that that's fundamentally incorrect. And one of the ways to see this is by looking at the different forms of commitment that people make to one another. And this book by Lawler describes these commitments as being instrumental. So these are things that are just have to do with the sort of practical things, like, you know, if I need to get a coffee and I'm in a new town, then I just want to pay money to a coffee shop and get my coffee. I don't care which coffee shop it is. If one coffee shop shuts down, I don't care. I'll just go to the next one. But as soon as I walk into one coffee shop and I have a little interaction with the barista, then my instrumental commitment turns into an affective commitment. Okay? So now I like, that's my barista. I like that guy. He likes me. Next time I go to the same two coffee shops, I'm going to be like, oh, yeah, I want to go to that one. And then if that one shuts down, I'm like, oh, no, my heart is broken. My favorite barista is gone. Okay? These affective commitments are much stronger, much longer lasting, and run much deeper. They're really what motivates humans to interact with one another. So they strengthen the bonds that make them longer lasting. They also increase trust between agents, and this leads to agents being able to interact with one another using shorter contracts, right? I trust this guy, so I'm going to do what he says. That allows agents to be more efficient, and I think this is regardless of the available cognitive resources, right? So a group that interacts using this is always going to do better than one that doesn't. Okay, so that's the end of it.
So I know lunch is probably almost here, if not already here, but are there any quick questions for like 4 minutes for Jesse?
Everybody's ready for lunch and Christmas.
So Jesse has some free time on his schedule this afternoon between 1 and 3. So if you do want to book some time to chat offline, you talk to me, talk to him. We can figure that out. Great. Thanks so much.
All right. Thanks. Hi. Yeah, nice to meet you. Yeah.